A groundbreaking discovery from the University of Oxford is reshaping one of science's most fundamental questions. Where did Earth's water come from? For decades, the prevailing theory has been that asteroids, icy, hydrogen-rich wanderers from the outer reaches of the solar system, delivered water to our young, rocky planet through a series of cosmic collisions. But now, new evidence suggests that this long-held assumption may have overlooked a far more elegant and even more inspiring explanation. According to this latest research, the ingredients for water were present from the very moment Earth began to form. In other words, our planet may have been destined for life from the very start. Using advanced techniques to examine the composition of a rare meteorite, scientists discovered that the very same types of rocky materials that coalesced to form Earth were already rich in hydrogen, one of the two essential elements that make up water. This is a stunning revelation. It suggests that water was not an exotic or foreign gift delivered from afar, but rather an intrinsic part of Earth's original structure, a natural and inevitable consequence of how our planet formed. The meteorite in question, found in Antarctica and named LAR 12252, is a pristine time capsule from the early solar system. Its close chemical resemblance to Earth's interior makes it one of the best analogs we have for what our planet's earliest building blocks might have been like. The research team, led by Dr. James Bryson and PhD student Tom Barrett, used a powerful X-ray technique to delve into the fine-grained structures of this meteorite. What they found was compelling. Specific regions of the rock, especially around tiny spherical inclusions known as chondrules, were extremely rich in hydrogen sulfide. The careful placement of these hydrogen-rich compounds deep within the structure of the meteorite rules out contamination from Earth and strongly suggests that this hydrogen was native to the material from the beginning. This hydrogen, when combined with the abundant oxygen already present in early Earth, could easily account for the formation of water, not just on the surface, but deep within the planet's interior. The implications of this finding are enormous and overwhelmingly positive. First and foremost, it significantly broadens our understanding of how common water might be on other rocky planets. If water is not a rare fluke delivered only under special cosmic circumstances, but a natural consequence of planetary formation from hydrogen-bearing material, then the universe may be teeming with water-rich worlds. This raises exciting possibilities for astrobiology and the search for life beyond Earth. If water was baked into Earth's formation, then it could be similarly embedded in the crusts and mantles of exoplanets orbiting other stars. Moreover, this discovery strengthens the idea that Earth's ability to support life was not just a fortunate accident. Instead, it paints a picture of a planet that was, in some ways, preloaded with the ingredients necessary for life. The emergence of oceans, rivers, rain, and ultimately biology itself might have been less about chance and more about chemical inevitability. It reframes our planet not as an exception, but as an expression of natural cosmic processes that favor habitability. This does not entirely erase the role of asteroids in Earth's story. The researchers are careful to point out that some water, particularly on the planet's surface, likely did arrive through asteroid impacts, as previous evidence suggests. But the crucial shift is in understanding that this delivery was additive, not foundational. The majority of Earth's water, especially the vast reserves hidden in the mantle and crust, was here from the start. This dual origin model is elegant and satisfying, blending new insights with past theories in a way that clarifies rather than contradicts. What makes this research particularly robust is its reliance on direct chemical signatures and isotope ratios. The meteorite matches Earth not just in its mineral content, but in the very specific types of elements and their isotopic fingerprints. These details give scientists confidence that they are looking at the actual stuff Earth was made from, and that their conclusions about hydrogen's presence are not speculative. It's the kind of meticulous, high-precision science that not only solves a mystery, but opens up a whole new realm of questions. Perhaps most thrillingly, this discovery does more than rewrite textbooks. It invites curiosity. If water was always part of Earth's design, when did it first condense? How did it move from the deep interior to the surface? How did this early hydrogen chemistry interact with volcanic activity, planetary cooling, and the eventual emergence of life? These questions now seem less like distant hypotheticals and more like puzzles we are finally equipped to solve. This new understanding brings a hopeful tone to planetary science. It tells us that water, the universal solvent and cradle of life, might not be a rare cosmic treasure hoarded by a few lucky planets. Instead, it could be as fundamental to planetary formation as iron, silicon, or carbon. It reinforces the idea that life, too, may be far more common than we imagined. Earth, in this light, is not an anomaly. It is a beautiful example of what the universe is capable of creating when the conditions are just right. And perhaps those conditions are more common than we dared believe.